So we're moving on to chapter 14. We're going to transition from randomness into probability. Okay? So probability is all about odds of making things happen. So let's talk about some of these. First, random phenomenon. This is when each attempt or trial generates an outcome where we know what the outcomes are, but we can't predict what the particular outcome is going to be. If you did it a lot, it would have a regular distribution. So in other words, the chances aren't going to change from one trial to the next. And we know what all the different outcomes of our trial could be, but we just don't know what it's going to be for certain. Probability is a number. It represents the likelihood of the occurrence of an outcome. Or in other words, if I did this over long term, what would the relative frequency be of a particular outcome? An outcome, that's just one of the possible things that could happen as a result of an experiment. So if I talk about an outcome, I'm talking about you ran the experiment one time and this is what occurred. That's an outcome. Probability, if I did this experiment many times, what would the relative frequency be of that outcome? So event. Event is a collection of outcomes that we identify in order to attach the probability to it. We'd say the probability of A. That's our example, P of A. So if I'm rolling a die, an outcome may be getting a 1. The probability of a 1 is an event. Okay? So let me try and rephrase that. If I roll that dice, I could get a 1. And if I rolled a die and got a 1, that is an outcome. If I rolled a die many times, I could figure out what is the relative frequency of a 1. 1 would be an event, and I could figure out the probability of that event. Now, a couple rules about probability. When studying this, we have to have a long series of independent events or trials. So this is when the outcome of an event doesn't influence the outcome of any other event or trial. Knowing that one thing occurred did not change the probability of the other. Our events need to be independent. Now, an example of this, rolling a single die twice. The result on the second roll is independent of the first. What I got the first time isn't going to change the chances what I get on the second roll. Now we can also have events that are not independent. Say I'm picking 2 cards from a deck one at a time without replacement. Since I pull out a card, I might have a certain chance of getting the Ace of Hearts. It's 1 out of 52. But if I set that card to the side, and now I go on and pull a second card out of the deck, I want to say, what's the chance now of getting the Ace of Hearts? Well, if on the first card I didn't get the Ace of Hearts, the probability is now 1 out of 51. But if I did get the Ace of Hearts on the first card, well, the probability is now 0. These events are not independent. Depending what happened on that first card could change the probability of the next card. Now, if you do pick, and that's if you pick the card and don't put it back in the deck. Okay? Now, this is why I said a red card. If you put the cards back in the deck and shuffle, the probabilities go back and you're independent now. But if you do it without replacement, they're not going to be independent events. So probability is empirical. It's a number. We can estimate it only when we observe many trials because of the law of large numbers. That just tells us that the long run relative frequency of repeated independent events eventually settle down to the true probability as the number of trials increases. And technically, it means when I've done an infinite number of trials, my relative frequency will be the true probability of that event. Short runs only give us a rough estimate. So if I flip a die or I flip a coin 10 times, I might get heads 5 times and tails 5 times. I also might not. If I flip it 100 times, I might get heads 50 times and tails 50 times. But good chance I won't get that exact number. But it's only going to give me a rough estimate of being a 50-50 chance. Because 100 compared to infinity is such a small number. So it's still only going to be a rough estimate. And this is also where we get the gambler's ruin, or more appropriately, the gambler's fallacy comes from. You might have heard this. Someone might lose a game multiple times, and then they'll say, oh, I'm due for a win. Well, let's say I'm flipping a coin, and that coin has come up heads 8 times in a row. Some people might think that since it's come up 8 times in a row, that means I'm due for it to come up tails. But that's not how probability works. If they're independent, what I get the first time has no effect on what I get the next time. So in other words, it's still a 50-50 chance I could get heads again. The fact I've gotten 8 in a row doesn't matter because they're independent. As long as your probability or events are independent, gambler's fallacy is when someone thinks just because one thing has happened a lot that suddenly the odds are going to change. No. If the events are independent, the probability stays, it remains constant. Now, we've got some probability rules. We have to obey these. If A is an event, then the probability of A, call that P of A, is a number between 0 and 1 inclusive, meaning it includes 0 or 1. If the event with probability of A is 0, that just means it never happens. The probability of A occurring is 0. It just can't happen. Alternatively, probability of A is a 1, it means it always happens. Every time I do it, this is going to occur. So it can never happen. It can sometimes happen, meaning the probability is somewhere between 0 and 1, or it can happen all the time, meaning it has probability of 1. Now we have some other probabilities here. The probability that A doesn't happen, well, that's going to be 1 minus the probability of A. That what we're saying is that all events, if I have some event I'm calling A, okay, let's just say it's the die. Now I'm rolling a die, and I call getting a 1 A. Well, when I roll a die, I'm either going to get a 1 or I'm not going to get a 1. And if I want to know the chance of not getting a 1, it's equal to 1 minus the chance of getting a 1. This is also called the complement of A, which can be marked as A apostrophe or A to the C. Now, probability S. S is a special term. This is going to be equal to 1. S, it's the sum of all the possible outcomes, all the different events. It's called the sample space. All the different outcomes that are possible is called the sample space. So the probability that we'll get something from the sample space, that's a 1. So for example, let's say I'm rolling a die. The distribution, the different values it takes on, well, the chance I get a 1, it's 1/6. Chance I get a 2, it's also 1 out of 6. Chance of getting a 3, 1 out of 6. Chance of getting a 4, 1 out of 6. 5, it's 1 out of 6. And a 6, it's 1 out of 6. So my sample space are all the possible outcomes. That's a 1, 2, 3, 4, 5, or a 6. The probability of any of those outcomes happening is 6 out of 6. And that's 1. I can add them all up that way. Okay. Now, next thing. 2 events are disjoint if they have no outcomes in common. And what's that talking about? Well, I'm not talking about disjoint. Okay. So a lumbar cycle joint. When I'm talking about 2 events where the same thing, where one thing happens, the other one can't. Okay. For example, let's say I'm rolling 2 die, and I'm going to make event A is the roll adds up to a 7, and B, the roll adds up to a 2. These events are disjoint. I can't roll 2 die and have them add up to 7, and at the same time, that roll added up to 2. That just can't happen. Those events are disjoint, or also called mutually exclusive. If one thing occurred, the other one couldn't. Now the addition rule, that's one of our big rules. This is an important one. If 2 events are disjoint, if they're mutually exclusive, then the probability of A or B happening is equal to the probability of A plus the probability of B. We can also write as probability of A union B, which is the probability of A plus probability of B. It just means the union. Now, in our previous example, we want to know the chances of certain things occurring. Well, I'm going to tell you right now, it's A was getting a 7, B was getting a 2 by adding 2 die up. This is what it adds up to. Oh, we have a little chart. We can prove it to ourselves. So if I wanted to get a 7, I could get a 6 and a 1 on die 2 and die 1. Alternatively, I could get a 5 and a 2. Or I could get a 4 and a 3, a 3 and a 4, a 2 and a 5, or 1 and a 6. So I have 6 ways out of 36. There are 36 possible combinations. 6 of those combinations will get me a 7. But to get a 2, there's only one way. There's one way out of 36 where the sum would make it 2. And we see here, I have 7 out of 36. Next rule we have is the multiplication rule. In order to use this rule, my events have to be independent. So if event A and event B are independent, so they don't affect one another, knowing event A happened didn't change the chances of event B, well then chance of A and B happening, so this is saying they both occurred at the same time, well that's equal to probability of A times probability of B. It's also, we write it as A, probability of A intersect B, which is going to be probability of A times probability of B, as long as the events are independent. Now this also can be called the intersection of A and B. So let's say I'm flipping a coin. Probability event A is getting ahead on the first coin toss. B is getting ahead on the second coin toss. We've said A and B are independent. Me getting ahead on the first flip doesn't change the chance of me getting ahead on the second flip. So they're independent. So the probability of getting a head intersect another head, so probability of A and B, both of them happening, well, that's equal to 1/2 times 1/2, that's 1/4. Now, we got somewhere to practice here. I'm going to jot down some of this information. Let's see what we can figure out. Let's say 40% of cars in Newport News are manufactured in the US. 30% come from Japan, 10% from Germany, and 20% come from other countries. So take a moment, jot these facts down. We're going to use this information. Now pause the video, get a copy down. Okay, so if you're still playing, you must have this information written down. So first thing is, if I pick a car at random, what's the chance a car is not US made? Well, that's the probability is not US made is 1 minus the probability it is US made. In this case, that's 1 minus 0.4 or 0.6. Well, let's see this. What's the probability a car is made in Japan or it's made in Germany? Well, that's probably it's Japanese or German. Those are independent, so it's going to be equal to the probability of, they're disjoint. You can't have a car that's Japanese and it was German. It was one or the other. These are disjoint, so I can just add them up. Probability of being Japanese plus probability of being German. That's 0.3 plus 0.1 is 0.4. Probabilities, we're usually going to do these just as a decimal. Okay? So let's try this. What's the probability that I see 2 in a row from Japan? Well, that's probability of getting 2 Japanese cars in a row. That's probability of Japanese intersect Japanese. 2 events happening. That's multiple events, so I get to multiply. Multiple events means we're going to multiply. Now the question is one car independent of another? Well, think about it. If I pull one car out of the parking lot or out of all of Newport News, does that really affect the chances of another car I pull at random out of Newport News? And no, it really doesn't. So I can multiply these. So it's going to be 0.3 times 0.3, 0.09. So the chance I'd get 2 Japanese cars in a row, selecting cars at random, 0.09. What if I ask about none of the 3 cars? I'm going to pick 3 cars at random. Cars being selected at random, what's the chance that none of 3 cars come from Germany? Well, no Germany means I'm getting probability of not German, intersecting a not German, intersecting not German again. I have multiple events, so we're going to multiply. Probability of not German times probability of not German times probability of not German, or 0.9 times 0.9 times 0.9, 0.729. How about at least 1 out of 3 cars is made in the US? So take a moment, think about this one for a second. Okay. Probability at least 1 of 3 cars is made in the US. Let's think about what could happen. If I'm pulling cars at random, let's talk about what could happen. So I'm going to select 3 cars. I've got that first car, well, it could be US made. On the other hand, maybe it's not US made. So these are 2 events so far. Let's get my second car. Maybe it was made in the US, or maybe it wasn't made in the US. But if it wasn't made in the US, there is another possibility. That first car could have been not made in the US, but it was followed up by one that was made in the US. So these are some possibilities we have so far. Let's say that third car, maybe it was US made. Or maybe I had 3 in a row that weren't US made. Or maybe I had a car that wasn't US made. But we got every possibility here. I'm going to tell you right now, we don't. So a lot of possibilities we're missing. A lot of possibilities. Okay. We could have gotten 3 cars that were made in the US, 3 cars in a row that weren't made in the US. We also could have gotten a not made, made, not made. We also could have had a car made in the US, followed by a car that wasn't made in the US, followed by a car that was made in the US. We also could have had not made in the US, followed by 2 that were. We also could have had 2 cars not made in the US, followed by the one that was. Or we could have had a car that was made in the US, followed by 2 that weren't. And let's see, 1, 2, 3, 4, 5, 6, 7. We're missing one combination here. Oh, let me see. Let's see. Made in the US, not made in the US. Made in the US, not made in the US. Made in the US, not made in the US. So we have a lot of options here. So US, US, US. US, US, not US. US, not US, US. US, not US, not US. So this tree can help me a little bit. This other side is not US. US, not US. US, not US. US, not US. We'll do these tree diagrams a bit later. I want to make sure we got all of them. So my first one, 3 cars made in the US. We have that. That would be following this branch of the tree. US, US, not US. US, US, not US. That's the one we're missing. US, US, not US. I thought we were missing one. Okay. Then, of course, we'll use our tree to double check. So US, not US, US. US, not branch 2. US, not US, US. There's 3. US, US, not US, not US. So US followed by 2 no's. US followed by 2 no's. Now we have our not US. Not US, US, US. There's branch 5. Not US, US, not US. So not, yes, not. Not, yes, not. Branch 6. Not, yes. Not, yes. And not. 8. So we have all our branches. Now our question was, at least one of the 3 cars is made in the US. At least one is made in the US. Well, that would give us, we could look at these. Let's get our highlighter. Oh, try that again. Is it being difficult? It looks like it wants to be difficult. Yep, it wants to be difficult. At least one was made in the US. Well, this one qualifies. Let's try it. What do we mean green? This qualifies. This line 6 qualifies. 3 qualifies. 5 qualifies. 7 qualifies. 4 qualifies. And 2 qualifies. So we could figure out the odds of each one of these. Car was made in the US, a 0.6 times 0.6 times 0.6. Not US, 0.4. I'm sorry, I got my numbers backwards there. And since these are multiple events, they'd multiply. We figured out the odds of that happening. Not US was 0.6, US was 0.4, not US was 0.6. These are multiple events, and they are independent. Knowing one card doesn't know another. The other thing is I can say each of these are disjoint, because if I get 3 cards that are US, I cannot at the same time have gotten 1 card that was from the US and 2 that weren't. So they are disjoint. There's no overlap. I can solve each of these and then add them all up. However, if you notice, there's something special about this. We have one, and only one, that didn't meet our criteria. So, 3 cars not made in the US. That's the only way I'd end up without at least 1 car being from the US. You're going to say at least 1? Well, the complement is none. None were made in the US. Because if that didn't happen, well, at least one of them was. Well, I know the odds of this. 0.6 times 0.6 times 0.6. And I know that one of these have to happen. And that adds up to 1. And I just remove what I don't want to have happen. So 1 minus 0.6 to the 3rd power. That's going to remove the one event I don't want to have anymore. Because the rest of the time, well, at least one of them was made in the US. So that's how we can solve it. We use the complement. At least one of the 3 was from the US? Well, that's equal to 1 minus none of them being from the US. So 1 minus 0.6 cubed, or 0.784. So let's think about another way we can do probability. What if I know the first Japanese car you see is the 4th one you choose? Well, that means we had to have a not Japanese car, and then the second event had to be a not Japanese car, and the third event had to be a not Japanese car or outcome, and then my last outcome had to be a Japanese car. Well, not Japanese car was 70% of the time, or 0.7. So I need 0.7 times 0.7 times 0.7 times 0.3, or 0.7 cubed times 0.3. Okay. These can take a little bit of practice. And I'm going to get us some links to where we can practice these. I got 0.1029. Now, this is all review. This material is all considered review. But I'm going to put some other links to some other videos on this and where you can do more practice. Because what I'm going to assign, read chapter 14. Add notes for items that you're still unclear on that came up inside chapter 14. And come to class with questions. Start the homework. The homework for this one comes up the textbook. It's questions 10 and 11, 21 through 23, and 27 through 29. I will also post some links to where you can go to practice other kinds of probability questions that cover if you need to multiply or if you just have to add events up. So I'll post links to both for if you're doing an addition or you're doing multiplication. To me, the easier to remember is if I have multiple events, I'm going to need to multiply. But if I'm just trying to see the odds that something happens one way or happens another, that's addition. So I'll bring you back to that screen. Our last little notes. Whoop. And I look forward to seeing you in class soon.